Hello, class. It's me, Mr. Garcia. I'm sorry that we have to do these virtual lessons over COVID, but I hope that you can gain the same understanding from this lesson that you would otherwise. I'm going to try to go in depth in things. There'll be a lot of questions for you to answer as we go along. So, yeah, let's get started. We're going to be going over the forces and interactions in engine mechanics. Let's get right into it. We have a few goals that we're going to be going over. By the end of this lesson, we're going to explain the concepts of force, motion, and interaction using examples from engine mechanics. So we're going to be able to define those. Knowing how an engine works, we're going to see the processes and equate them to force, motion, and interaction. And we're going to analyze how these different forces interact to produce motion inside of an engine. And we're not going to get to this today, but students that do complete this lesson would be able to assemble a basic engine using electric or a chemical engine using these things they learned today. So that they'd be able to apply their understanding of forces and interactions to design a simple engine model. But mostly we're going to be dealing with these two top goals. So key terms that we'll need to know are force, motion, interaction, engine, stroke, and work. And if these sound scary, it's okay. They're really not so simple. Once we engage in them as they happen inside of an engine, I think you guys will be not so scared of them. So a force is just a push or a pull that can cause an object to accelerate, change direction, or deform. Now's a good time to mention these questions here. We're not going to be answering them all, but the questions throughout this lesson would be for the students learning. Like most of the learning that happens would happen because of these questions. They'll get information here. They can then use to answer these questions, hopefully with my guidance. I'll ask the questions. They'll spit out a half right answer. We'll build on it from there. And hopefully the whole class would kind of pool together their knowledge to answer these questions and get everybody accustomed to it without, the lecture just droning on forever. But that's going to be what this sounds like because I'm not going to be asking the questions and answering them because it would just take too long. But yeah, this is where the learning happens. Is all the questions. There's a lot of them, but I'll explain. I'll do my teaching portion, my direct teaching portion by defining things, describing equations and stuff. But know that these questions are for the learning. So force means this. Motion means a change in position of an object over time. An interaction is the way that different objects or systems physically affect each other. An engine is just a machine that converts fuel into mechanical energy. Stroke is one complete cycle of the piston in a four-stroke engine. We'll see how that happens, but just know that a stroke is one cycle of the piston. And work is the amount of energy transferred to an object when a force is applied to move it over a certain distance. So work only occurs when force is applied over a distance. If there's no movement, there's no work. That'll come up later. And throughout this day, I've answered all these questions to understand these better. So, more questions. Let me move myself so you can see them. What do we know about forces and interactions already? How do engines exploit Newton's laws to generate motion? And how can we design an elementary engine ourselves? They'd answer these questions and hopefully get primed for the content. So these are our NGSS standards right here. Go ahead and pause to read them. I'll move over so you can see them. And our AG standards are the B through 10. We're actually going through 3 of them despite not learning how to construct an engine. So yeah, welcome to Forces and Interactions and Engine. So move myself here. What happens inside of an engine? We need to know actually what moves, how the car moves because of the engine to really understand how force comes into play here. So the 4-stroke cycle is how most engines work, a car, a tractor, an airplane, anything you can think of that moves something probably is the 4-stroke cycle. And it just consists of these 4 steps. So a stroke is literally just the piston moving from here to here. That's one stroke. The piston moving from here to here. That's one stroke. So the intake stroke is when air is taken into the engine and fuel is injected into the air. It kind of moves around. Then the compression stroke happens at the bottom of this, so you can air comes into the engine, then the piston comes back on the compression stroke, and it compresses the air-fuel mixture really, really tight. Just know that it's pressurized during the compression stroke. And during the power stroke, a spark is lit right here, and you can see it like pushes the piston down. This is where the energy is generated in the engine when the piston is just pushed down like that. And there's only one other place for it to go. It moves back up after that. We call that the exhaust stroke, and that burned fuel is spit out, and now we have an empty cylinder ready for the compression stroke to happen again, the intake stroke, sorry, to happen again. So questions they would answer after that is, how do engines convert this energy, whether it be electrical or chemical, into mechanical energy, movement of the car? And how does the engine deliver that rotational force to the wheels? So, are there any other types of engine? Yes, we call it a two-stroke engine. Theoretically, you can have any number of strokes. There could be whatever steps happening in the engine, but the most efficient one that we use today is the four-stroke. There's also a two-stroke engine, and you might be thinking, isn't two-stroke more efficient because there's less steps? But no. I mean, this is the most dirty, crude engine that we have. The four-stroke cycle is like a refined version of the two-stroke. So the two-stroke cycle combines the compression and the ignition into one stroke, and the exhaust and the intake into one stroke. And basically what that means is that as the fuel is exhausted after it ignites, at the same time it's exhausted, you have new fuel coming in. And so you have old fuel mixing with new fuel, and that kind of dirties the fuel that actually sparks. You don't get as clean of a burn as you get inside of a four-stroke engine down here. So since this fuel is mixed together when it's exploding, how does that affect the upstroke? Let me show you this. How does this affect the upstroke? Like, how does that make the fuel burn worse? Why is that less efficient? So, first equation, F equals ma. It's just Newton's second law of motion. It equates the force applied to an object. It means the force applied to an object is equal to the mass of an object times the acceleration of said object. And this is important to us because we can actually equate the amount of force generated from this explosion, the force applied by this explosion, to its mass and its acceleration. And from there, we can find the energy of the car and equate the actual motion of the car to these explosions inside of the engine. Might seem enigmatic. You might be thinking, how does a car move? By me pouring gasoline into it, but it's this. It's just force equals mass times acceleration. It's a very simple formula, and it happens every single time you start your car. So it's very simple to work with. If it feels simple, F equals ma, it's because it is very simple. It's a very simple mechanic that engineers have exploited to get our cars to move. So if we know a piston weighs 2 kilograms, each piston is 2 kilograms, and we know that it accelerates at 15 meters per second squared, we can ignore these in kilograms. We just need to know that 2 mass times 15 acceleration equals 30 newtons of force. That's it. Each piston generates 30 newtons of force as the fuel is exploded. The students would do this on their own. How much force is generated directly from the fuel exploding against the pistons? Hopefully they're like, oh, simple. I could totally work with this. Then we knock them back down with some more equations. The work energy theorem, which basically just equates work to the change in kinetic energy. And this is actually how we find the motion of the car is related to the motion of the pistons. Because we can find, the distance the car moves is equal to this kinetic energy inside of the pistons. And yeah, we got to know D is distance of force applied, W is work, and F is force. This is kinetic energy. V just stands for velocity. This is the change in velocity. This is change in kinetic energy times mass. It's very simple to work with. So I would sort of quiz the students here. How can the pistons have kinetic energy as it's moving, or as the engine is moving, but the car itself isn't moving? This would be like when it's idling. You have your foot on the brake at like a stop sign. The car is like, you can still see the rev counter at like 1,000 revs, but there's no movement in the car. How does that happen? We know kinetic energy isn't zero because the pistons are moving, but why is there no work? And it's because the car isn't moving. We'd hopefully come to that conclusion. So the engine only produces work when the car moves. That's the goal. So here's momentum and how momentum is related to force and time. Momentum is just a measure of how easy it is to stop something. Heavier objects carry more momentum. We hopefully relate the small pistons move super quick inside the engine to generate a lot of momentum forward. We'd also know how the car generates stopping force. Very simply, it's the brakes squeezing down on the caliper. It's like friction. And hopefully we'd use these equations to see how the car. How can we use these equations to see how changing the momentum of the car corresponds to the engine process? So when we slow down the car, we press on the brake, the revs slow down because the wheels physically, if the wheels are slowing down and the wheels are connected to the engine has to slow down to correspond to that change in momentum. And the way that we equate all of these together, hopefully you can see it, is this monster of an equation down here. They wouldn't need to use this, but this is just an equation that equates them all, and we would derive this in class through all of the equations that we have here, all of these guys. So here's our practice problems that we would do in class. These are easy. You wouldn't need to use this, but it's here if you need to work through it, find all the other variables of the equation. But here's 5 practice questions for the class. After that, just to wrap up the lesson, they want to read it. Maybe I would read it to them. I think this is very long, but this is mostly for them to refer back to if they want to quickly remember what the lesson was. Maybe if they want to study for a test or whatever. But here's where I would ask them for questions, see if they have any big gaps in their learning. And this is the end. This is where they would submit their answers into the front basket as their little exit ticket to validate their learning. And yeah, have a good day, class. From your friendly teacher, Joey Garcia. So yeah, my lesson plan.